So today let's explore what's inside of an electronic fluorescent starter. Somebody asked for this. It says electronic safety starter for 18 to 75 watt fluorescent tubes. So let's see how does it work and what's inside of it, including the schematic, and let's also explain why these were actually used to retrofit the standard starters. Of course, I treated myself some dumpster fluorescent fixtures to be able to test it, and let's also explain the fixture and what the starter does in it. In a traditional fluorescent fixture with an iron inductor or magnetic ballast, the mains comes in. There can be an optional compensation capacitor to compensate for the power factor, which is otherwise on the inductive side. Sometimes it's just a small interference capacitor instead of a big compensation capacitor, and sometimes it's not installed at all. Here is the inductor with an iron core, limiting the current of the lamp or fluorescent tube, because the discharge basically has a certain voltage drop, which actually goes a little bit down with more current. It has a negative resistance, so it can't be connected straight to mains, and using an inductor to limit the current is less lossy than using a resistor in a series. The fluorescent tube basically contains a mixture of gases, typically argon with some mercury, and the discharge in it produces some visible and also some ultraviolet light, and the ultraviolet part of the spectrum is converted to visible light using the phosphor on the inside of the glass tube. And when the tube is already ignited, the voltage drop of it is about 50 to 150 volts. But to ignite it you need a spike of a higher voltage, several hundred volts typically. And also for an easier ignition, the electrodes can be preheated. They are made of a resistive wire coated with an emissive layer, and preheating them during the startup also reduces their wear. When you turn the fixture on, the current goes through the inductor, through the filaments and through the starter. The tube is not yet ignited. The starter contains a small capacitor and also a glass tube with electrodes and filled with gas. It's like a neon lamp, but instead of normal electrodes, it has electrodes made of bimetal stripes. And when the tube is not ignited, it does not pull the voltage down after the inductor, so there is enough voltage to make the gas glow in the starter bulb, and the glow heats the electrodes, and as the bimetallic electrodes get heated, they bend towards each other and touch, and this basically makes the lamp short. And now it passes a high current through the inductor and the filaments, and they preheat, they glow orange typically, and after a couple seconds the electrodes cool down, and they no longer make contact. And when they suddenly separate, it also creates an inductive spike from the inductor, and this spike of a voltage higher than the mains voltage ignites the tube, and then it passes current. Now the current goes through the gas in the fluorescent tube. And of course, once the fluorescent tube is ignited, it draws current and pulls the voltage down after the inductor. So the voltage is no longer enough to make the starter bulb glow, so the starter doesn't trigger again and doesn't try to restart an already started tube. And the reason the traditional starters were sometimes retrofitted with the electronic ones is that the standard neon glow or gas tube glow starter is sort of random. It sometimes makes several cycles before it manages to start the tube. And this can cause more wear to the tube and also the well-known annoying blinking, or very cool blinking, depending on your taste. Now let's take a look at an example of the traditional starter. One is in this fixture and it's falling apart, which is sort of convenient. Let's show it in operation and then let's explain why it's acting so randomly. Let's plug the fixture in, and you can see it glowing, it's blinking and it started. Now let's try to show it with less light in the room. And a closer look. Now the electrodes are separated, turning the lamp off and back on. Now they glow, short, start the tube, and can I get it better on the camera? Turning it on. And that's it. One more try. Turning it on, it glows, makes a contact, starts the tube, and the tube is basically started when the electrodes come apart. And the reason the traditional starter is sometimes creating blinks in random intervals several times before it manages to start the tube is that the timing of it is random. It runs on AC voltage, and this small capacitor in the starter, besides interference suppression, also sort of sets the preheat time. With no capacitor, the electrodes would basically just touch and almost immediately separate, because when they touch, the glow immediately disappears and they start cooling. But because there is the capacitor in parallel which is charged, it basically discharges when the electrodes touch and they slightly weld, and as they cool down and try to separate, it takes some time to cool enough to develop enough force to separate them. So basically the electrodes slightly welding is what creates the preheat delay. But because there is AC voltage in it, the voltage on this capacitor during the moment the electrodes touch is completely random. And the more voltage on it, the more the electrodes weld, and the longer they make contact. Because as they cool down, they gradually create more force trying to separate them. But of course sometimes they weld too much and they never separate, and the tube is basically stuck in the preheat mode, and you can just see a constant glow on the ends of the tube. And of course the welded starters were sometimes fixed just by knocking them or tapping them. But of course when the electrodes get welded too little, the preheat time is too short, the electrodes don't have enough time to warm up, and after this of course the tube is less likely to ignite the moment the electrodes separate. So basically one factor of randomness is the voltage on the capacitor when the electrodes touch, which sets the preheat time. And of course another random factor is the current through the circuit when the electrodes separate. And again, because it's an AC current, the current can be anything from 0 to the square root of 2 times the average current during the moment of electrode separation. And of course if the current at that moment is not high enough, the inductor doesn't produce enough of an inductive high voltage spike to ignite the tube. And so if the preheat time is too short or the inductive spike is too low, the starter has to repeat the process. And that's the typical random blinking of fluorescent tubes during their startup. And that's why in some fixtures they were retrofitted using the electronic ones. And the preheat time is controlled much more precisely, and also the connection opens, probably during the peak of the current. The standard one, starting with blinking. Now let's try the electronic one. And when I turn it on, it preheats and turns on with no blinking. And of course when you remove the starter after the startup, it has no effect, it still runs. But when I turn it off, and back on, it actually starts capacitively anyway because it's a short tube. But the longer the tube, the less likely it is to start up without the starter. Now it's actually not starting without the starter, it's quite random. And of course also turning it off and back on in a short time leaves it heated and ionized, so it's more likely to start without the starter. But it's also not good for the electrodes when it's starting cold. The electrons emitted from cold electrodes are removing atoms of the metal. Let's test it in the other fixture. This is the standard one. How do I remove the starter that fell apart now? It's out. Now the electronic one. Preheating. And starts with no blinking. And of course I like this green, sustainable, eco-friendly, energy-efficient symbol on it. And a couple years later it's an inefficient, hazardous waste. The opinions are changing so quickly these days that nobody's safe here. And Osram is made in Germany, it's made in Poland, it's made in absolutely everywhere. Made in Russia, imagine that. Importing tubes from Russia, also something that's never going to happen again, probably. And of course you can also start fluorescent tubes by just momentarily shorting the terminals for the starter. It's actually cold restarting when turned off for just a short time. Shorting the electrodes, it's preheating, and now it's started. But now of course let's open the electronic starter. It has a circuit board in it, and Does it come out? It does, and some SMD resistors, no other SMD components, and on this side seems like a discrete bridge rectifier plus another 2 diodes, some fuse, I guess, a transistor, maybe a triac, some resistor, 2 capacitors, another transistor here. Let's try to actually reverse engineer it. This is a fuse, 2 amps, 130 degrees Celsius, and the input terminals basically go via the fuse and a bridge rectifier made of discrete diodes, and there are no transistors and no chips, just thyristors or SCRs and passive components. And all the semiconductors in it are sort of weird types. Here's the bigger thyristor and the smaller one. The small one is just a low power, low voltage one, and this one is the main one, switching the preheat current. And this weird diode says just PSR on it, and good luck trying to find the datasheet, but I guess it has to be a Zener diode, because otherwise the schematic doesn't make any sense. I guess it's a high voltage Zener, and when the fluorescent tube is not yet ignited, there is basically a full minus voltage going in, and at this voltage this one passes current and charges this capacitor and triggers this thyristor. And then this one is on and passes current through this diode, and this actually creates a voltage drop. This diode basically regulates the voltage, and from this low sort of regulated voltage this capacitor is slowly charged, and this does the preheat timing, and when this one charges enough the small thyristor triggers, and basically discharges this capacitor and pulls the voltage down here, and basically removes the current from the big thyristor's gate, and this one turns off. And this is when the fluorescent tube strikes. And then the input voltage is lower, so it's not enough for this Zener, so it doesn't trigger again. This Zener sort of replaces the threshold voltage of the neon lamp in the traditional starter. The threshold has to be somewhere between the minus voltage and the fluorescent lamp operating voltage. And of course when this one turns off, there is probably the inductive spike, and this spike is too short to charge this capacitor, so it doesn't re-trigger the thyristor. And this resistor discharges this capacitor and prepares it for the next cycle. And of course this diode also adds a voltage drop to the voltage drop gate to cathode of this thyristor to ensure that the gate threshold voltage is higher than the voltage drop of this one, because otherwise this one can't turn this one off. And of course I was sort of expecting a transistor in it instead of a thyristor, because a thyristor or a triac typically stays on until the zero crossing of the current. But if it was turning off during the current zero crossing, the inductor couldn't produce a high voltage spike to strike the fluorescent tube. So I decided to look at the datasheet of the thyristor, and the datasheet of it says fluorescent tube lamp starter SCR. It's basically a thyristor specially designed just for tube starters, which really surprised me. But it actually makes sense because a typical thyristor or triac wants to have a low holding current to ensure it stays on until very close to zero crossing of the current. But this one wants the opposite, a high holding current. This one actually says more than 175 milliamps, which means it's turning off long before the zero crossing of the current, and so a high inductive spike can be produced. So that's it, a very interesting thyristor for just this purpose. 2 amps, 400 volts, and 1.5 kilovolt peak, and a sensitive gate 1.5 milliamps. And the datasheet even shows an example schematic, which is virtually the same as the schematic I reverse engineered, and yes, this diode is a Zener. It's basically the same thing, other than there is no fuse here. I took the Zener from it and let's test it, let's measure its voltage drop. I just rectify mains voltage, smooth it, and then it goes via a combination of resistors to pass about 1 milliamp. And mains in a breadboard is always a brilliant idea, isn't it? And at 1 milliamp the Zener drops about 195 volts. And 200 volts at 5 milliamps. Not measuring it for too long because this is 1 watt of dissipation. So we can call it a 200 volt Zener. And what surprised me, there is no capacitor in parallel to the input, like in the traditional starters. And this sort of suggests that this capacitor is not for interference suppression. If it was, the electronic one would probably have it too. I couldn't really find a clear answer why traditional starters have the capacitors in them. But many years ago I tried to remove it and then the contacts were clicking much faster. And that's why I think it's to slightly weld the contacts and make the preheat longer. And I guess these electronic starters are not retrying to strike the fluorescent tube. Let's just connect it with a series 60-watt light bulb to mains and lights up. And goes out and does not retry to start it. Disconnecting it, reconnecting. It probably makes one attempt and doesn't keep restarting to prevent worn-out fluorescent tubes from constantly blinking, which is the typical problem of the traditional starters. And they keep infinitely retrying, and these are some old ones, Czechoslovak Tesla and some Poland. I took the capacitor out of this one and let's see how it behaves without it. It was clicking quite rapidly, and this one glows orange, it probably has neon in it. Some of them glow purple or white or bluish, they might use other gases. Let's measure the capacitor. It's about 10 nano. You can probably measure it inside of the starter because the neon lamp has no effect at such low voltage from the meter. 5 nano, 10 nano, 10 nano, 5 nano. It's always in this ballpark. Let's put the capacitor back for comparison. The capacitor's back and let's see. It definitely doesn't click as quickly. Now the electrodes have a tendency to stay together longer. When they touch far enough from a voltage zero crossing, so the capacitor is actually charged at that moment. And some people suggested that the capacitor with the parallel neon lamp forms a relaxation oscillator. Let's try to connect it to mains via a 22 kilo ohm resistor and see the waveform on it. Plugging it in, it's lighting up. Not enough current for it to click, I guess, and let's see. I don't really see much of an oscillation here. Maybe a little bit here, actually. At the beginning of this half cycle, but not here for some reason. And that was an old starter doing the same measurement with a modern one. Not much happening here. The gas just strikes and pulls the voltage a little bit down. And this one behaves more symmetrically. And drops about 200 volts, because it's a 220 to 240 single starter. And there are also starters for 110 to 130 volts, which can also be used for 220 to 240 volt mains and 2 fluorescent tubes in a series. And these drop less voltage, this one just 100 volts. And an old series starter dropping about the same as a modern series one. And the voltage on the 18 watt tube when it's running. And you can see the negative resistance here. The half cycles are bending in, not out. It drops less voltage at more current. Which is not the case for the starter lamps. They work in a saturated mode to allow the high voltage striking pulse. And let's see the inductor in the 15 watt one. Actually I have one identical here, or almost identical. Elektrokovina made in Slovenia. And the whole thing in Hungary, and it was apparently neutraled, grounded using neutral. Here until 96, you had just 2 wires and a neutral doubled as ground. And this still remains in older buildings and DIY wirings. And a nice preheat glow. Now let's try an isolation transformer, the electronic starter connected to it via an inductor in series and the oscilloscope measuring on the starter. And let's plug it in. A pulse. Now the thyristor is on. And then a series of high voltage pulses and they fade away, and now it's just minus voltage. The main thyristor is now off. And this basically simulates a worn out fluorescent tube which no longer ignites. Let's try it zoomed in. 1 half cycle. Thyristor on, preheating, the pulse is fading away and just a sine wave minus voltage remains. Let's try a 36 watt inductor. A short pulse on. Pulse is fading away and just minus voltage. It seems to be acting more or less the same. Now zoomed in. 1 half cycle, thyristor on, preheating. Now the pulse is fading away and maintenance voltage only. And the pulses are about 13 or 1400 volts. 1426 volts. So it's not just one pulse as I was thinking. This schematic is not easy to simulate in your brain. It seems like the thyristor is fully on during the preheat, and then it's gradually reducing its conduction angle, like a triac dimmer turning down, but this one is not turning off in the zero crossing. This one is turning off mid-half cycle. After the preheat, it's gradually reducing its conduction angle as this capacitor discharges, or as this one charges maybe, and the small thyristor actually turns the big one off mid every half cycle. And if the tube ignites, there is no longer enough voltage for this zener to conduct and there is nothing to turn it on. And if the tube doesn't ignite, I guess eventually this capacitor charges enough to keep this one always on, which keeps this one always off, and finally this one is not turning off in zero crossings because this capacitor keeps it on. And this is basically how it gives up when the startup is not successful. And of course the video got bloody long, but if you've made it that far, please consider subscribing, supporting this channel on Patreon or using the thanks button. And big thanks to all of you who already support me, because this channel couldn't exist without you.